Hi, this is my video number 21. So in this video I'll continue the nonlinear system of the non-autonomous system of equation. In the last video I've given the definition on the uniform stability, which, if you recall that definition of stability, we have given any epsilon positive, you can find delta positive, satisfying x and minus x1, the norm of x and x1 less than delta, that satisfies x minus x1 less than delta epsilon. Okay, now let's prove a couple of results. First thing, I prove lemma. So the first result that we have, this lemma, all solutions of x dot atx are uniformly stable, if and only if there exists a positive m such that norm phi t phi inverse t phi inverse s, this is less than m. For t naught less than s less than t less than infinity, where phi t is any fundamental matrix, where phi t is a fundamental matrix. Now let's prove this. First of all, you prove that way, which means there exists m satisfy all these things, then the solution is uniformly stable. Remember that in this at this point you need to remember the definition of what is the uniformly stable. Okay, now given the solution, the proof given the solution, xt x t t naught x naught and any fundamental matrix phi and any fundamental matrix phi, then for any t, then for any t1 greater than t naught, so we have xt, this is equal to phi t phi inverse of t1 x t1. This is standard matrix. We can have x, that one give you identity, and then you got that again, so it satisfy the solution, the system given. Okay, so now if we consider another solution, x1t is equal to phi t, phi inverse t1 x t1, x1 t1 should be x1 t1. Then given any epsilon, so what we can do from here, if I can we can subtract these two, all right, and take a norm and see what happens, right? Given any epsilon, given any epsilon positive, then we have x minus x1t, and take the norm of that, xt minus x1t, right? So this equal to that minus of that, so we have phi t, phi inverse t1, you factor that out, and what left is x t1 minus x1 t1. Okay, now this part here given in the here, this which is less than m, so we need to choose what is x t1 minus x1 t1. So this one is already given m, so therefore we may choose x t1 minus x1 t1 less than epsilon over m. That will give us xt minus x1 t1 less than, all right, so this part here we have m, this part we have less than m, less than epsilon over m, so we have epsilon over m, so that gives us less than epsilon. So therefore we can conclude that a solution are uniformly stable. Yeah. So therefore the solution are uniformly stable. Okay, now what about the other way around? If you are given, because here in this lemma we have if and only if, which means we have if and only if. Where is it? Here we have it if only if, which means the first part that we prove from right to left means we have m positives, satisfy that, and then we show that the solution are uniformly stable. Now if we have the solution is stable, we need to show that there exists m which satisfy this thing. Okay, so in order to do that, we begin with the hypothesis. The hypothesis says that there exists m with, the hypothesis says that the solution is uniformly stable. Okay, so since the solution x t naught 0 is uniformly stable, then what we have uniformly stable, which means given any epsilon positive, we can find delta positive such that we have x t naught x naught minus x t naught x1. Okay, so I think in this case let's consider we have x as a solution, and we may consider another solution, let's say x and x1. Yeah, x, so let's say let's put this as x naught So this is s x naught. All right, and we consider another solution x t naught x1. This is s x1 are the solution. Yeah, uniformly stable. So therefore we have this thing. We take the difference of that, and we know that x is given as phi x. So we have from there, you can use those the fundamental matrix phi t, phi inverse t1. This is x naught minus x1. Okay, now this less than epsilon, we know that this because of the uniform stability of the solution, we know that this part must less than epsilon. So which means all these things less than epsilon. Remember that we need to find that. Okay, so we may choose, in this case we may choose x naught minus x1 less than epsilon delta. Okay, here you can consider delta if you want, or you can consider delta over 2 if you want. So if you choose that, so what will happen from that? Okay, so we have phi t, phi inverse t1. Okay, that one less than delta, so that's delta. All this less than epsilon. So therefore we have phi t, phi inverse t1 less than epsilon over delta. So this is your m. That's your m. So therefore there exists m that satisfy those things less than m. The proof n. Okay. Now let us proceed. We prove the result for the system x dot atx plus ftx. Okay, where we assume the matrix A. Yeah, we assume the matrix A for t greater than t naught and ftx satisfies ftx is continuous for norm of x less than some number a, and this is for t greater than t naught, and number 2, there exists a continuous non-negative function. There exists a continuous non-negative function alpha t such that integrate ab alpha t dt less than infinity, which means is integrable, and the norm of f tx less than alpha t x. Okay, and this condition implies that the xt equal to 0 is the solution to our system. Yeah, this condition implies that xt equal to 0 for t naught t infinity is a solution of let's call this 1, solution of 1. Okay, now let's prove the result. So we have a theorem. Suppose that the solution of x dot equal to atx are uniformly stable, and asymptotically stable, satisfies the condition 1 and 2 here. Yes. Satisfies condition 1 and 2, then the solution xt 0 of 1 is uniformly stable and asymptotically stable. Uniformly stable and asymptotically stable. Okay, so we're going to prove this. So what can you say before we prove this? What can you say about this theorem? So this theorem says that if you're given that solution, that system, and this is system here, we have x, atx, and f, where f satisfy this condition 1 and 2, f continuous, and there exists a function, non-negative function alpha, that satisfy those which is integrable, and also the norm is bounded by some numbers. Then if the solution of that system, then the solution of that system uniformly stable and asymptotically stable, so does for the solution of that system. Which means if you want to find the stability of the solution of that system, it is enough for us to study the system of that, the solution of that system. Okay, by having this, provided that f satisfies condition 1 and 2, then we can conclude, make a conclusion for the solution of the system that we are looking for. Now, how to prove this? The proof is a little bit lengthy, but still okay. Let's prove this. Okay. So since all solutions of the linear system are stable, since the solution of the x dot equal to atx, this is a linear system, are uniformly stable, which is given in the hypothesis, uniformly stable, so we can use the definition of and as well the previous lemma, as well as the definition of uniform stability. So there exists a constant m such that for any fundamental matrix phi, such that for any parameter matrix phi, such that we have phi t phi inverse of s less than m for t naught less than less than s less than t less than infinity. Okay, so if t1 greater than t naught, if t1 greater than t naught, which means between s and t we have some more t1 there, then any solution xt, then any solution xt that satisfy x t1 less than some number a, okay, satisfies the relation, you have xt equal to phi t phi inverse t1 x t1 plus integrate t1 to t. You can see you can find this the solution can be written as that in the proof of the previous theorem. Phi t phi inverse of s f s x s ds. Okay, for t1 less than t less than some number t, where xt less than a for t1 t t. Okay, so using that we take the norm of that expression, norm to the left and norm to the right. So what we have, a norm of xt that less than norm of this less than m, so we have that less than equal to m, then we have xt x t1, and for this we have exponent of m integrate t1 to t alpha s ds. Okay, so where do we have this? This is come from in the previous notes. Where is it? Yeah, we have this. Okay, okay, so from there, so we have that and we take the norm, so we got those things. All right, and this is less than m x t1 exponent t1 to t t1 to infinity alpha s ds. This is equal to some number k that x t1, because this one is bounded, is given that I showed earlier. Now given epsilon with epsilon greater than number a, then we may choose those x, t1 norm of that less than epsilon over 2k. The reason why, because we want to show all those things less than epsilon. We want to show that x is less than epsilon, which implies that if we do this, implies that xt less than epsilon over 2. So this is from that, because we choose xt1 less than those things, you substitute into there, so we have this. And you can use a similar argument with the previous theorem that I have proved, yeah, from the previous theorem. From the previous theorem, we have xt less than epsilon over 2 for t greater than t1. So therefore, if we combine those things, we have the solution is the solution xt, the solution xt 0 is uniformly stable. Uniformly stable. Remember that you want to uniformly stable means we want to show the solution, the norm of that less than epsilon. So we have shown that from there, this is less than epsilon. Now, to show the asymptotically stable, asymptotically stable means if you take the limit of the solution, it goes to 0. So, yeah, that means asymptotically stable. So to show for the asymptotically stable, what we have, the limit, yeah, for asymptotically stable, if you take the limit t goes to infinity, those fundamental matrix, it goes to 0. Yeah. Hence, given any x naught such that x naught less than some number a, and also given any epsilon positive, we can find some number that exists, let's say t naught greater than small t naught, such that phi t x naught less than epsilon for t greater than t naught. This is definition of the asymptotically stable. Yeah. So for the solution, xt equal to x t naught x naught, we have for t greater than t naught, capital T naught, the norm of xt less than phi t x naught plus t naught to t phi t phi inverse of s f s x s ds. Okay, and which give us this part less than epsilon. We know that this part less from that, this part less than epsilon, so we have epsilon plus, and this from our condition, yeah, so plus t naught t, we have m alpha s x s ds. Yeah, we can write this because f, for that norm of f is less than some alpha and phi less than number m. So, and x is still there. We have x. So we have those things. So you can use from ground wall inequality again. I think you can find what ground wall inequality is. Ground walls inequality. We have xt less than epsilon exponent m t naught infinity alpha s ds. This equal to epsilon, let's say some number L for t greater than t naught, because that part is bounded. So that's, we have L. And since epsilon is an arbitrary, and L here in this case not depend on epsilon, of course, because that one is bounded, it's free of epsilon. So you can consider that. So we have, from there we can conclude that as limit t goes to infinity x t, that equal to 0. So therefore the solution is asymptotically stable. So therefore xt equal to 0 is asymptotically stable. Okay, so why we do this? Why do we do this, or how do we get this? Because you can choose epsilon as small as you want, small enough that close to 0, then we can get those things. All right, so with those theorem, how do we got the or how do make the conclusion on the solution of the nonlinear system of non-homogeneous non-autonomous system, which is based on the conclusion on the linear parts. Okay, if it linear case is stable and asymptotically stable, where f satisfy the condition that we mentioned earlier, then the same conclusion can be applied to the nonlinear case. Okay, so with that I stop here for this video. See you in the next video. Bye.